Hi everyone, and welcome to the second of two videos going through some past exam questions on the topic of the equilibrium constant, Kp. So here we've got another calculation question. Again, it just wants us to calculate Kp. So we're going to approach this from the same method that we've seen before. We're going to set this up with our ICE table. So the first thing we're going to do is write out the equation. And then we're going to set up our table here with the initial amount. I'm just going to put the letters here to change and how much we've got at equilibrium. So we mix together 1 mole of CH4 and 1.4 moles of H2O in a container. The mixture is heated, allowed to reach equilibrium, and the equilibrium mixture contains 0.2 moles of CH4. So at equilibrium, we've now got 0.2 moles. Okay. So therefore, the amount of CH4 has gone down by 0.8. And because here it's a 1-to-1 ratio with the H2O should also go down by 0.8. And so therefore there will be 0.6 moles left at equilibrium. It didn't tell us how much of these we had initially, so we're going to have to assume that they were 0. And that's why it hasn't mentioned them. Then again, if we apply the ratio here, it's a 1-to-3 ratio, so it should change by 3 times as much as this. So this should then be plus 2.4. And it's a 1-to-1, 3-to-1 ratio, so this should be plus 0.8. Okay, so now we've got the equilibrium numbers of moles. If we want to calculate Kp, we now want to do the mole fractions and the partial pressures. So if we go for the mole fractions next, to work out the mole fraction, remember, it's the number of moles of that particular species divided by the total number of moles. So we need to add this up and work out the total number of moles. So let's just put a total in here. Let's do that. So that's in 3.8. So the total number of moles is 4. So then we just need to do each of these divided by 4. So I am just going to do this on the calculator in case I mess this up. So we've got 0.05, 0.15, 2.4 is 0.6, and that's going to be 0.2, isn't it? Okay, and so then finally we want to calculate the partial pressures. So you get the partial pressure, remember, what you do is you do the mole fraction multiplied by the total pressure. Okay, so we're going to do each of these and times them by 30. So 0.05 times 30 is 1.5. 0.15 times 30, 4.5. 0.6 times 30 is 18. And 0.2 times 30 is 6. So those are all our partial pressures. Now we need to then actually calculate the value of Kp. So we're going to need to write the expression for Kp first. So Kp is going to be, remember, it's always products over reactants. So we've got the partial pressure of H2 cubed times the partial pressure of CO. And we're going to divide that by the partial pressure of CH4 times the partial pressure of H2O. So therefore, now we need to be careful we get these in the right places. So H2 is 18, so it's 18 cubed times 6 divided by 1.5 times 4.5. Okay, and then look at this. This is going to be a big number, right? The top is much bigger than the bottom. So we're expecting a pretty large value here for our Kp. So let's just work this out. 18 to the power of 3 times 6 divided by 1.5 times 4.5. And we're getting 5,184. Okay, and remember with the equilibrium constants, there's no kind of, is it a sensible value? It could be a really big value, it could be a really small value. It can't be negative, obviously, that doesn't make sense. But here this looks reasonable, right? We said it's going to be a big number, is a big number. You know, if I'd calculated this and it'd come out as 0.2, I've done something wrong, haven't I? But this is telling us that the equilibrium is far to the right-hand side, which is what it's telling us. Like, we've got much bigger partial pressures than these, so that does make sense. They are going to want us to work out the units. It doesn't actually mention that anywhere, but they always want you to work out the units. So just watch out for that. Even though it doesn't say it, do it anyway. So we're going to put the units in. So it's going to be atmospheres, because we've used atmospheres here. Again, you don't need to do any sort of conversion from atmospheres to pascals or anything like that. So it's going to be atmospheres cubed times atmospheres over atmospheres times atmospheres. So therefore we've got atmospheres to the power of 4 divided by atmospheres to the power of 2. So it's going to come out as atmospheres squared. Right, at the bottom here, there's another little question here. This is looking at a different equilibrium. So it's saying, why is this equilibrium a heterogeneous equilibrium? We can see that just from the state symbols. So the reason it's heterogeneous is because the species have different states. That's all it wants. And then if we're going to write the expression for Kp, right, this is why they've linked it in. This matters, the fact that they're in different states, because if we're doing Kp, we're ending up calculating partial pressures, aren't we? You can only have a pressure of a gas, can't you? You can't have the partial pressure of a solid. It doesn't make any sense. So these things are not going to be involved in the expression for Kp. So Kp is going to be products over reactants. So we've got Fe we're going to ignore because it's a solid. We are going to have CO, so it'll be the partial pressure of CO to the power of 4. Ignore that. Divided by the reactants. Well, the reactants are both solids. So actually, that's it. It's just the partial pressure of carbon monoxide to the power of 4. Okay. Moving on. We've got another little multiple choice question here. They do seem to like multiple choice questions with Kp. So here we've got our equilibrium. We've got the number of moles at equilibrium. What is the partial pressure of SO3? Okay. So before we can work out the partial pressure, we need to know the mole fraction. So remember, the mole fraction is the number of moles of that thing. So it's the moles of SO3 divided by the total number of moles. So we're dividing it by 0.4 plus 1.2 plus 2.4. So we need to work out that mole fraction first. 1.4 plus 1.2 plus 2.4 is 4. Oh, okay. 0.4 divided by 4 is 0.1. And so then if the total pressure is 250, we're then going to multiply them. So the partial pressure is 250 times 0.1. So it's going to be 25 atmospheres. So it's going to be B. They always seem to be B as well. Right, last question that we're going to look at here is a slightly different one. This is no calculations. This is more of a wordy type question. So they've given us some data here, and it's saying predict with a reason whether the forward reaction is exothermic or endothermic. So to do that, we just need to look at what the data is telling us. So let's just write out what's happening. So we're seeing as the temperature increases, what happens to the value of Kp? As the temperature gets bigger, Kp gets smaller. Look, so it's gone from 10 to the power 12 to 10 to the power minus 1. So as the temperature's gone up, Kp is decreased. So if Kp is decreased, it means the equilibrium must have shifted to the left. It's gone more towards the reactants. Okay, if we had more products, we'd have a bigger value of Kp. So as temperature increases, Kp decreases, so the equilibrium has shifted to the left. So when you increase the temperature, according to Le Chatelier's principle, the equilibrium would try to decrease the temperature, and it would shift in the endothermic direction. Well, our equilibrium has shifted to the left, so left must be the endothermic direction, so the forward reaction must be exothermic. Right, and then this is sort of the most common wordy question that you get. It's a bit of an awkward one. They've increased the pressure of the equilibrium mixture, but they've kept the same temperature. Explain in terms of Kp. This is kind of the giveaway. Whenever they say this in a question, it's the same type of question every time. So if you ever get in terms of Kp or in terms of Kc, if you're doing the that version of the equilibrium constant, it's always the same question. It's usually a 3-mark question. How are we going to expect the equilibrium position to change? Okay, so if we increase the pressure, let's look at what effect is that going to have. So increasing the pressure, that's going to affect all of the values of Kp, isn't it? Let's actually write our expression for Kp. If that's our equilibrium expression, let's write Kp. Kp is going to be the partial pressure of NO2 squared over partial pressure of NO squared times the partial pressure of O2. Now, if we increase the pressure, the total pressure, then all of these partial pressures will go up, won't they? Because they're all calculated as mole fraction times total pressure. So if the total pressure is getting bigger, all of these values are getting bigger. But if all of these values get bigger, it's going to have more of an effect on the bottom of Kp than it is on the top, because we've got values that are overall to the power of 3 on the bottom. We've got a power of 2 here and a power of 1, and we've only got a power of 2 on the top. So if all these numbers get bigger, it's actually going to make Kp smaller, because the increase on the bottom is going to be more than the increase on the top. So that's the first thing that we're going to say. Increasing the pressure increases the terms on the bottom of the Kc expression more than the top. On Kp, sorry, on the bottom of the Kp expression more than those on the top. So that should make Kp smaller. But what else is going to happen? Well, if we've increased the pressure, if we go back to our equilibrium, if we increase the pressure, the equilibrium is going to shift to decrease the pressure by Le Chatelier's principle. So it would shift to the side with fewer molecules of gas in order to decrease the pressure. We've got 3 molecules of gas on the left and only 2 molecules of gas on the right. So the equilibrium would shift to the right. So we can talk about that as well. Increasing the pressure would shift the position of equilibrium to the right. Because there are fewer moles of gas on the right hand side. And what effect would that have? Well, if we've shifted to the right, we've got more NO2, so that's going to increase the terms on the top of Kp. So therefore, what have we said? We've said we're going to increase the terms on the bottom of Kp more than on the top, but then we're going to do something else which increases the terms on the top. So overall, the value of Kp doesn't change. And that shouldn't be a surprise to us, right? Because equilibrium constants, remember, are only affected by temperature, and we're keeping it at the same temperature. Okay, so nothing is going to change the value of the equilibrium constant other than the temperature. Okay. This is a bit of an awkward question. It's always 3 marks. Hopefully you can see where you get your 3 marks for. There's 1 mark for talking about what actually happens to the values in the Kp expression. So the idea that, yes, they've all increased, but we've increased the bottom more than the top, because that's where we've got higher powers. Then there's a mark for the Le Chatelier's principle, which way is the equilibrium shifted. And then finally for saying overall Kp doesn't change.